Did anybody see that video yet? You guys don't look at videos anyways, right?
I started to.
Okay.
Wait, the video's online?
Yeah.
Yes, I have something.
So, if this is our week, December 1st through the 7th. If you look at the videos for the week, I would normally have a video and then a little space and another video. So this is where today's video is going to go. This is where Tuesday's lecture is, but then I added another video on that particular problem. And so this video would have the complete explanation, and I hope the audio is okay. But here's where we need to put L into this function, and what we didn't do and should have was broke down those functions as piecewise functions, because there are piecewise functions. There's a shift and there are piecewise functions. So when we break up these piecewise functions, we can call this g and g prime, the derivative. And instead of taking the derivative of that complicated looking relationship between f of t and u of x minus t, or f of t minus a and u of t minus a, instead of taking the derivative of that, if we can look at this as a piecewise function, we can take the derivative in pieces. By taking the derivative, you can easily evaluate it at any point you want. And we want to evaluate it at L, where L is bigger than 1/2 L, so you're going to use that bottom function, and this is where we get these non-zero values. And so those non-zero values go back, and then you put it back into your system of equations to solve for C1 and C2. Now, in putting it back to solve for C1 and C2, you would have a system of linear equations in C1 and C2, because C1 and C2 are not being raised to any powers or anything like that. And it's non-homogeneous in the sense that there's a non-zero on the other side, because these don't have C1s and C2s, so we bring it over to the other side, and then we have this particular system. Now, there's a variety of ways for solving for this system. One is to solve for C1 and then solve for C1 in one equation, plug it back into the second equation, solve for C2, and then bring it back to solve for the C1 originally. Or the way I ended up doing it here is to use Cramer's rule. Now, Cramer's rule is a nice little rule that we may have learned in algebra, but it's dealing with matrices. So by using Cramer's rule, I was able to get the solution a little bit quicker. And so here's Cramer's rule to get the solution for C1 and C2. And after getting C1 and C2, I take that and plug that back into the equation. So we've successfully used the other boundary, y of L and y1 of L, or y prime of L, to solve for those unknown constants. Okay? All right. So, like I said, this video is available in it's available in our web access site, so you can view it if you're interested, and so you can come up with the answer for your homework. Or you can not view it. I don't care. All right. So I'll say see video. So today this gives us a free pass now to move on to the next chapter, chapter 8, which is dealing with systems. And I think I jumped on that last time and put on a few slides about systems of linear equations. Now, the theory behind this is that we're going to transfer our study of differential equations and making it look like a system we're going to transfer our study from these differential equations to matrices. Okay, so if you're in linear algebra or have taken linear algebra, then there's going to be a lot of these terms that should be familiar to you, or maybe you forgot already from yesterday's lecture, I don't know. But we will need to know a little bit about eigenvalues and eigenvectors. So those eigenvalues and eigenvectors in this class, I won't formally define them, but I'll just talk about the method of finding them, and I will refer to them as eigenvalues and eigenvectors. But the point is that you want to just be able to solve for those things, and then from your solutions be able to come up with your solutions to the system, the actual differential equation. Okay, so the basic idea is a system of a linear system of differential equation is going to be a set of equations, a set of differential equations, and we have a set of unknown functions, x1 through xn, that we're going to be solving for. And there are going to be these coefficients, and for our sake in our class, for simplicities, and since this is the end of the semester, we're just going to focus on constant coefficients. But technically, these coefficients could be functions of t or whatever the variable is. But anyways, these coefficients, whether they be constant or functions, get placed into the matrix of coefficients that we have here. So if this is our set or our vector of functions, and this is our coefficient matrix from the system, and this is another set of functions that's given, if we take the derivative of this vector, is just taking the derivative component-wise, and then if we take a times x, you're taking this matrix A and applying it to this vector, or you can think about it as matrix multiplication, and then you're going to get exactly this portion over here. And then there's a plus f. If you have a bunch of non-zero functions, then you have a non-homogeneous set. And if you have a homogeneous system, then these f functions will all be 0. Okay. I know it's kind of hard looking at this with n by n matrix stuff, but we're going to, when we do examples, we'll take a look at this, and we're just going to do up to 2 dimensions. All right, I think the next page here gives us some examples of the beginnings of these types of differential equations, and what we want to do is we want to be able to write them out in matrix form, or we want to be able to go from matrix form to a bunch of equation forms. So let's take a look at this system over here, number 2. If we want to write this in matrix format, all we have to do is we want to peel apart the matrices and the vector functions. So we can think about x, y, and this is technically, they call it capital X. So that's x, y. So x prime is going to be the derivative of each of these components. Right? Now, we take a look at the body or the right-hand side of the system, and we want to just peel out the matrix A out of this. So, again, we just look at the coefficients, 4, -7, 5, and the one corresponding with the y is 0. And the idea there is that if we take A and apply it to the vector x, I guess maybe if I don't call it a vector, if I just call it a matrix, I can erase the arrow on top. Doesn't matter. 4 minus 7, 5, 0 is A, and apply it to the vector or the matrix X. And if you do this matrix multiplication, you know how to do matrix multiplication, right? It's the first row times the first column. In this case, it only has one column. And so that is going to give us 4x minus 7y. And then if we take the second row and that column, it would give us a 5x plus 0y. And so that's exactly what we have on the other side. So we can say that the x prime is equal to this, the y prime is equal to this, and then that's the system. So I think in terms of answering their question, if they want us to write this in matrix form, we would probably just say, I guess my answer here would be, I don't know, x prime, y prime is equal to 4 minus 7, 5, 0 times xy. And this is equivalent to saying the x prime matrix A times x. Okay? And when you do this 1 or 2 times, you'll get the hang of it, and then you'll just peel out the coefficients, and it'll be a piece of cake. So the second one, they want us to write the system without using matrices, and right now it's written as matrices. And so let's see if we can rewrite that without the use of matrices. And assuming that x is equal to the matrix xy, or the vector xy, I'll do this in a couple of steps, but you don't have to. Again, do this enough times and you'll take a look at this and be able to write the equations down a lot quicker. But let's see if we could just take our time for now. We got x prime and y prime for the left-hand side of the equation, and we got 4, 2, minus 1, 3 times xy, plus now we have a vector times a scalar, and what happens here is that we can just combine this into one vector with nothing hanging outside. So 1 times e to the t and negative 1 times e to the t, just so I can have that as a big package. And then I'll just do this matrix multiplication now. This is going to be 4x plus 2y, and then a negative x plus 3y. And then we can continue on and just combine the different components. And then finally just be able to rewrite this as dx dt, or just x prime, I guess. Dx dt is equal to 4x plus 2y plus e to the t, and then dy dt is equal to minus x plus 3y is minus e to the t. So now we've successfully transferred from a matrix to a pair of equations that constitutes a system. So here's a linear system of differential equations. Any questions? Good. All right. You're comfortable with dealing with, pulling out a constant, or in this case it's not a constant, technically it's a scalar. If you have a vector or a matrix, you can pull out a scalar, or you can multiply in a scalar, and this is how it would look like. Any questions? Now, compared to last lecture, this is pretty light, right? It's pretty easy. I mean, it's going to get harder, but you guys still have the same expressions that you had last time I saw you, which is kind of glazed and confused. All right. We'll move on. Okay, I did mention in the previous page that if those functions were zero, you can consider the zero vector, we have a homogeneous system, which is what we're going to focus on in this class. Just to formally define a solution vector, a solution is going to be a vector of functions. So now they call it a vector instead of a matrix. Or maybe I changed it into a vector. Anyways, it's a set of functions whose entries are supposed to be differentiable functions, and they would satisfy your differential equation. And then they also introduce this idea of an initial condition, and what they're doing here is just introducing a bunch of notation that would stuff that we've seen already. But now since we're talking about a system, we're talking about not just one function, but a set of functions. And when we're talking about initial conditions, not just one condition, but a bunch of initial conditions. So you can think about these initial conditions as x1 of t naught is equal to gamma 1, x2 of t naught is equal to gamma 2. So that's what this relationship is. And so instead of writing out all those initial conditions for each of the different functions, since we were successfully able to write the set of functions as a vector, we might as well write all these initial conditions as vectors as well. So what we're doing is we're establishing the language of vectors and matrices to represent these differential equations, because we will be using vector and matrix techniques to solve for these differential equations. So this problem over here is asking us to verify that the vector is in fact the solution to the given system of equations. So we want to check if this is a solution. And your solution is written in this way. Now, your differential equations is written in this way. I think for us to be able to check if a solution for a differential equation is going to work for us, we want to write this by solving for x and y separately, and then we'll put x and y here. So let's see if we can do this problem. So if you rewrite your x vector, you're really looking at 1 times e to the minus 5t and 2 times e to the minus 5t. And from here, you should be easily be able to identify your x and your y functions. So your x should be e to the x, or e to the minus 5t, and your y should be e to the 2e to the minus 5t. Now that you know that, you just plug it into the differential equation, into the system. So they want the derivative of x and the derivative of y. So let's figure those out. Let's call this x prime of t. And the derivative of this is e to the negative 5t times minus 5. And then the derivative of the y is minus 10 e to the minus 5t. So if we take these and plug it back into this, we would then get the x prime is minus 5 e to the minus 5t, and this is supposed to be equal to 3 times x, which is e to the minus 5t, minus 4 times y, which is 2 e to the minus 5t. And if we simplify that, we get 3 minus 8, negative 5, so that checks out. And then now we put the y prime, which is negative 10 e to the minus 5t. This is supposed to be equal to 4 times x, and x is equal to e to the negative 5t minus 7 times y, and y is 2 e to the minus 5t. And so you have 4 minus 2 times 7 is 14. 4 minus 14 is negative 10, and they both have e to the negative 5t, so that works out also. So that's how you would verify that your solution exists. Okay, and notice how the solution is written. A lot of times we're going to write our solutions like this with a function on the outside, but remember that that just works out to just distributing that e to the negative 5t, that scalar function, into that vector. Good? Still easy? All right, here's a bunch of other theory behind this thing that we're not really going to, I'm not going to stress so much over it. Existence of a unique solution. This is equivalent to the existence and uniqueness theorem, but for a system. As long as the entries of the matrix A and F are functions that are continuous on some common interval that contains your initial condition, then we have a unique solution that exists. So you're guaranteed a solution. So that's the first part. Say that in words and you can take it or leave it. Superposition principle. This is the same superposition principle that we've had, except now we're dealing with this as vectors or matrices. So suppose we have a set of solutions, x1 through xn. These are vector solutions to our system. Then the linear combination of all those is also going to be a solution. Okay, we've seen that when we started to study higher order differential equations. We introduce one solution, but if we have a second order differential equation, we need another one. And so this is how you can find your other one. A set of vectors is said to be linearly independent if their constants not all exactly 0, such that this linear combination of these vectors are equal to 0. So we define linear combinations when we talked about the Wronskian. In fact, we use the Wronskian to figure out whether something is linearly independent or not. So this shouldn't be anything new. It just looks a little bit different because instead of looking at individual functions, we're looking at vectors. Speaking of the Wronskian, we're going to use the idea of the Wronskian as a way to check if these vector solutions are linearly independent. So the Wronskian, last time when we used it, we had to take derivatives and then put them into this matrix, and then we found out, and then we mainly stuck with a 2 by 2 matrix, which is what we're going to do here also. We're going to stick with 2 by 2 matrices. But since our solutions are already in vector form, what we're going to do is we're going to line up your Wronskian as columns. So these are going to end up being columns of a matrix where we're going to take the determinant of that matrix, and if that determinant is exactly 0, then those solutions are linearly dependent. And if the determinant is not 0, then the solutions are linearly independent. So that's what this criterion is saying. So the big deal is that those solutions, those vector solutions, since they are vectors, we're just going to place those vectors as column vectors in a matrix, and we're going to find the determinant of that matrix. Now, we know how to find the determinant of a 2 by 2 matrix. I'm hoping that for the sake of doing the homework, you guys can find the determinant of a 3 by 3 matrix, but I'm not going to worry about that. Okay, questions? All right. So I think that's all 8.1. Just laying out this information for you. Now, in 8.2, they begin by looking at a system, and then already within that system, they start implementing the idea of eigenvalue and eigenvectors. And I don't know, maybe I should talk a little bit about eigenvalues and eigenvectors briefly, or I could just do what the book does and just follow along with the stuff. All right, so what we want to do is we want to find solutions for these things. And like I said, for us, we're just going to stick with the homogeneous part, homogeneous linear systems. And also, we're just going to try to lay low with just 2 dimensions. And maybe we'll take a peek at a 3-dimensional problem, but in general, we're just going to look at a 2-dimensional problem. All right, maybe I should talk about, should I talk about eigenvalues first? Let's talk about eigenvalues first. Maybe I should type this. My handwriting is not at its prime. Especially if it's new material, right? Eigen. How do you spell eigen? Yeah. So eigenvalues and eigenvectors. So in some matrix theory, there's an interesting relationship between a matrix. Let's just say let A be a matrix. And for now, let's take a general n by n matrix, but we're going to be mainly working with a 2 by 2 matrix. let A be an n by n matrix. So it's quite possible with the matrix multiplication and the application of vectors that if there exists a scalar, and usually the scalar, the variable that they use for a scalar is the Greek letter lambda. Scalar lambda and a vector, and here they use x or v's. I guess it doesn't really matter. I'll use a v. Such that A applied to x, the vector x, is equal to lambda applied to the vector x. Then that number lambda, the scalar, is called an eigenvalue. And with the eigenvalue, there is what we will say a corresponding eigenvector x. Anybody speak German? No, I'll just say, what's the eigen? What's eigen? Well, identity would make sense. I mean, this is the relation here. We have a vector. So this is actually something that's pretty incredible, because this is a matrix times a vector, and this is a scalar times a vector. It's kind of weird to think about a matrix times a vector equaling a scalar times a vector, but a matrix times a vector happens to be a vector, and inherent, eigen, proper, individual. Thank you. So eigen means like proper or owner or yeah. So anyways, yeah, kind of like identity. So the idea that this matrix has this property where you apply a vector to it and you get another vector. Oh, there's this graphic of eigen stuff that I was supposed to show my linear algebra class, and I keep forgetting. So I'll show you, because it doesn't really apply to this class. Where would it be? Eigen picture. So I showed you this, and then somebody said, "Can you animate it?" I said, "I don't know." So I animated it. So the idea behind an eigenvalue and eigenvector is that those black vectors in the middle are the vectors x. And then what I did was I applied the vector x to the matrix and then attached it to its head. And if it's going in the same direction, same size, or if it's just going in the same direction, then that would be an eigenvector. Now the size of this, let's stop it somewhere where it's going in the same direction. At this point, for example, it's going in the same direction, but the original vector x in green there is a little bit shorter than the vector blue, which is the matrix applied to that vector. And so the eigenvalue for this would probably be a number less than 1 so that this can shrink down. Or, I'm sorry, a number bigger than 1 so that the green vector can look like the blue vector. So this is we did it for 12 here. We could make it a little bit more exciting and do it for like 36. It looks even cooler, especially when you animate it. Then you have it go around and you can try to figure out which one is the eigenvalues or the eigenvectors. Let's go. What's 36 times 2? 70, 72? Let's double this. Let's make it really fun. Ooh, does that look cool? I'm just wasting time now. It's stopped. Too much in the memory. Make it go faster. Oh, that's slower. Faster. Whoa. Cool. Stop. All right, stop. Seriously. Stop. Uh-oh. Abort. I'll just put it in the background. Stop. All right. It doesn't even go back there anymore. Oh, control. What is it? I don't know. Kill. And goodbye. It's not going away. All right. Anyways. Oh, boy. What's this? Go away. All right. Back to the idea of eigenvalues and eigenvectors. So this is what we want, or this is the definition of an eigenvalue, eigenvector. Now, the task is for us to try to find the eigenvalue and eigenvector. So guessing with a graphing program like Mathematica is not really the best way to do that. And so we want to try to find it symbolically. And the way to do this is is to, well, I don't know if this will make sense, but if we bring everything to the other side and set it equal to 0, I want to be careful about this. This is 0. This 0 is not the number 0, right? Since AX is a vector, lambda x is a vector, so 0 has to be a vector. So we want to make sure that we're dealing with vectors here. Now, in just with our algebra training, we look at something like this and say, oh, it's equal to 0. Boy, I'd sure like to factor out x, right? So now we're going to have a big problem here, because if I factor x out, this totally is not going to make sense anymore, because I have a matrix minus a scalar, and that just, you can't subtract the matrix. You can't do anything. If you have a matrix and a scalar, you can multiply it, okay, so something will work there, but you can't add or subtract matrices and scalars because those are two different things. So how do you think we can deal with this? Well, if we make lambda into a matrix, how do you make lambda into a matrix? If you make lambda into a matrix by multiplying it by the identity matrix I, you guys know what the identity matrix is? Identity matrix depends on the size of the matrix, but identity matrix we'll have 1s in the diagonal and 0s everywhere else. And if we do that, now at least we're dealing with a matrix here, a matrix A minus another matrix lambda times I. And then now you're dealing with something that you can legally do. So this is going to be the way to find it. And the way to find this is that now there's this whole talk in linear algebra about null space and stuff like that that I'll try not to use in this class. But let me just tell you the way to find this. And for now, let's not worry about x. Let's not worry about that vector x. Let's worry about finding lambda. And to find lambda, what we want to do is you know that this is A minus lambda I is actually a matrix. And so if we take the determinant of that matrix, what we're going to have, what we should have, is a scalar, and the scalar will end up being a polynomial. So we take the determinant of this and set it equal to 0. And now this 0 is not the 0 vector, it's just actual 0 because it's a scalar now. And then we'll just solve for lambda. So we'll get the eigenvalue that way. All right, so I think we should do an example where we're just looking for the eigenvector and then proceed on to find the eigenvalue, and then we'll apply it to the idea of a matrix. So what should we do? We should, I was going to say make up a matrix, but whenever I make up anything in this class, it usually turns bad. Let's just make up a matrix. So let's let A equal to just some matrix 3, 5, 4, and 1. And let's see if we can find the eigenvalues. Let's make one of them negative. I'm getting afraid now about the kind of solutions we're going to come up with. Let's take our matrix 3, negative 5, 4, and 1, and let's find the eigenvalues for this. So remember the setup, and I'll just jump to this last bit that we came down to. And the setup is to find the values. We want to take the determinant of A minus lambda I, and I'll write that as the determinant of A. A is 3 minus 5, 4, 1, and then lambda I is 1 in the diagonal, so if I multiply lambda by that, I'm going to get lambda 0, 0, and lambda. So I want the determinant of 3 minus lambda, negative 5 minus 0, 4 minus 0, and 1 minus lambda. And do you remember how to find a determinant of a 2 by 2 matrix? With the Wronskian, we did that already, right? So it's multiply the diagonals minus the product of the wings. So we have 3 minus lambda, 1 minus lambda, minus 4 times 5 is 20. negative 20, so I'll put negative 20 here, and then we'll make that positive in a minute. Okay? So now it's just another second degree polynomial. It's just another quadratic. The lambda squared becomes positive lambda squared. The middle term is negative 1 minus 3, so the negative 4 lambda. And then the last term is positive 3, and then we add 20 to it. Lambda squared minus 4 lambda plus 23. And this is why I shouldn't make up problems, because I'm going to get some weird answers now. Yeah, and this, we want this determinant to equal to 0, and this is where you would solve for it using the quadratic formula. Ideally, if this is a nice setup problem, you can factor this. I don't think you can factor 23, so we're kind of screwed. And at least it's not complex. I hope not. Right? And so lambda is going to equal to negative b plus or minus the square root of b squared minus 4a. It is complex. Really? All right. Well, this would be your eigenvalues. You have two eigenvalues. Turns out that it's going to be complex eigenvalues, so let's actually do a problem from the homework or something. That would give us a non-complex eigenvalue. But that's the process. Good? All right. Oh, it's gone. Uh, 8.1 and 8.2, yeah. Oh, I didn't want to do that. I hear they're actually solving for these things now. Maybe we'll take a linear algebra problem. What section's eigenvectors? 4.3. All right, let's take this one. And let's do this one where we have to find the eigenvalue, and then this time let's continue on and find the eigenvector. I didn't want to find the eigenvector for complex numbers, although you might have to do that later on. I haven't decided yet. So let's get this set up. So we want to know what a minus lambda I is equal to, and we want to take the determinant of that. And remember that lambda I is lambda's in a diagonal, so maybe I'll put it down here. Lambda I is equal to lambda 0, 0, and lambda. So that when I subtract component by component. So I got a negative 2 minus lambda, negative 1 minus 0, 0 minus, or 1 minus 0, and negative 4 minus lambda. Now, if you're in the linear algebra class or you've seen this enough times, you can just, this should be a quicker step. So the determinant of A minus lambda I will end up being the product of the diagonals minus the product of the wings. And then now let's multiply it out again. So I'll take the lambdas first, and then we want to add 1, so that becomes 9. Lambda squared plus 6 lambda plus 9. So now, like I said, in most of the problems that you'll be doing, you'll get nicer numbers like this where you can factor. You can factor this, right? Is it 3? So lambda plus 3. And it's important to note that this was a 2 by 2 matrix, and this was a second degree polynomial, a quadratic. And so it might be just good to note that this has multiplicity too. This -3 solution has multiplicity too. Okay? All right. So finding the eigenvalue is okay now, yeah? That's the easy part. Now we want to find the eigenvector. And so I want to bring back that equation. A minus lambda I times x is equal to 0. So if we bring back this equation, this x that we're looking for here is an x vector. So in the 2 by 2 case, it has an x and y component. And we can look at this as a system or whatever. But what we're going to do is we're going to put that lambda that we got, and if you had 2 different ones, you would do this twice. You would put the lambda that you got for your eigenvalue into this equation. So we have A minus -3I x is equal to 0. So you're essentially going to be solving for a system of linear equations with x and y. Now, how's that going to look like? We have the vector, or we have the matrix -2, 1, or -2, -1, 1, and -4. That's A. And I might as well just add this. Can I just add this? This would be a plus. And then 3I is going to be 3, 0, 0, 3. X is equal to 0. So this would be -2 plus 3 is 1, -1, 1, and -1. Whoa, look at that. So from here you can branch off to a couple of things, and since we didn't really discuss a lot of matrix theory in this class, you can just go back to the system of linear equations, and since we're really going to be dealing with 2 by 2 matrices for the most part. You can pull this together into another system of linear equations which you can try to solve. Or you can keep it as a matrix. I don't know if you guys are familiar with doing finding the null space or finding solutions of system using augmented matrix and row reducing. In either case, either way you approach it, you're going to lead to a system or some solutions. So let's see. If we row reduce or if we combine the equations, we're going to get just one equation. So all these will really just come down to one equation, whether you do it using a system of equations or matrices. You really come down to one equation. And when you're coming down to one equation, you want to describe this using vectors. So what you're going to do is you're going to let t, so by the way, if you have something like this, you know you have two equations and two unknowns. You have like 3 possibilities. One possibility is that the two lines will intersect at a point and you'll get exactly one solution. Another possibility is that these two lines are parallel, in which case you get no solution. Or this is our third possibility, where the two lines are exactly the same, and then you have an infinite number of solutions. So the system yields one line. And so this gives us an infinite number of solutions. Not necessarily. That's not always the case. But that's a good observation. This is multiplicity 2, and so we're going to get one vector out of this. It's possible that you could get 2 vectors out of this that are different. And in this case, we're only going to get one line. So it's possible that we can get another line out of this, 2 lines out of this, but in this case, we're only going to get one. So what we're going to do, and this is where it gets tricky, and if you haven't taken linear algebra, you really have to be careful about how to do this. We're going to let y equal to some parameter t, so that x minus t is equal to 0, or that's just saying x is equal to t. And this is now the solution that you're looking for. You're looking for the vector x. And so the vector x is actually the vector xy, which is the vector tt. Both positive? Yeah? Which can be seen as t times vector 1, 1. Not quite a unit vector, but yeah. So in any case, this is the vector that we're looking for, 1, 1. Actually, any multiple of that should work. But we'll just deal with this vector 1, 1. Okay? So what you're saying now is that the eigenvalue lambda is equal to -3 has a corresponding eigenvector of 1, 1. Okay? All right. So that was fun. And we can do this for 3 or 4 or 5 dimensions, depending on the size of our matrix. Let's see if we can actually, I was going to say we can put in the answer to check our answer, but this is my version, so the answers are already there. All right, I won't worry about that. So, back to our class. After having gone through the process of finding eigenvalues and eigenvectors, it turns out that the theory for differential equations is actually going to bring us to solving for eigenvalues and eigenvectors. So here, let's take a look at let's take a look at the theory now for our class. So in dealing with, well, let's think back again to the very first week of class where we had a nice simple first order linear differential equation. A is equal to, or A prime or whatever, A prime is equal to K times A. That was our simplest differential equation, and then we found that the solution for this is some constant times e to the k, kt. So it seems like in a lot of differential equations that we're dealing with, especially the linear differential equations, our base function, our go-to function, is like the exponential function, right? So that's what we're going to assume here as well. When we're dealing with a system of linear equations, we're always going to be involving our exponential function. So we're going to suppose that we have a solution, and the solution can be written this way. K1 times e to the lambda t, K2 times e to the lambda t up to Kn, whatever. And so K, if we just wrap up all these constants, these coefficients, as a vector, we can take a look at this vector times e to the lambda t. So if this is supposed to be a solution to this differential equation, we can just plug in all that information to our differential equation. Well, the process is shown here, but if we plug it in, if we look at x prime, that's x1 all the way up to xn prime, the derivative of each of these things. And if we take a look at that derivative, the derivative, since this is a k, is just a bunch of constants. It's in vector form, but it's really just a bunch of constants. So this will end up looking like constant times the derivative of e to the lambda t, which is lambda e to the lambda t. So that's all your derivatives now, compactly written like that. And this is supposed to be equal to a times x, right? So x prime is equal to a times x. So we worked out what x prime was. What's a times x look like? A times x is really going to look like a times the solution that we are assuming is k e to the lambda x, or lambda t. Right? And so what they do is they just pull from these two expressions, they get rid of the e to the alpha, e to the lambda t. So k lambda e to the lambda t equals a k e to the lambda t. Get rid of the lambda t's, or e to the lambda t's. And then we have a matrix times a vector equal to a vector times a constant. That's exactly the definition of the eigenvalue that we had. So a, k equals lambda k. And so this is your lambda is your eigenvalue. And k, a matrix or a vector, depending on how you look at it, is really your eigenvector. Okay, so all we need to know is A, and once we know A, we can find eigenvalues and eigenvectors, and then now we just have to form our solution properly. So here they introduce that polynomial that we had to solve for. It's called a characteristic polynomial, and that's what it's called in linear algebra as well. So if you run into that sometime in the future, it's really just a characteristic polynomial. It's a way for you to find the eigenvalues. Elio? This one? Yeah, these are x primes. Actually didn't use it, but that's how it would look like. All right, so in our case with, actually in any case, but in our case with just 2 dimensions, we're going to be looking at quadratic polynomials. Quadratic polynomials, we have 2 distinct real roots, or we can have 2 repeated real roots, or we can have complex conjugates. So next time we'll take a look at those cases, and we'll see how your solutions will look like depending on what case you have. But this is coming down to solving for characteristic polynomials to find your eigenvalues. Okay, that's enough for today.